Agonists are molecules or ligands that interact with a receptor and cause it to influence a cell's behaviour. Receptors are specific molecular targets, usually part of a protein, to which the agonist binds to produce its biological effect. Receptors can be found on the surface of a cell membrane, in the cell cytoplasm, or in the cell's nucleus. Agonist drugs mimic the action of natural signalling molecules, such as neurotransmitters and hormones. There are different types of agonists that do this in varying ways, known as full, partial, inverse, biased, super, and co-agonists. I will explain what defines each of these agonist types. Agonist drugs bind to the receptor site on an inactive protein. That causes a conformational change in the protein, which causes it to become active and generate a cellular response. The type of response depends on the nature of the receptor protein, which can be a ligand-gated ion channel, a G-protein coupled receptor, an enzyme-linked receptor, a cytoplasmic receptor such as a steroid receptor, or a nuclear receptor. When studying an agonist, it's normal to begin by measuring the amplitude of the response it produces at different agonist concentrations or doses. A graph is then constructed with the y-axis recording the amplitude of the response. In this case, each response is plotted as a percentage of the maximum observed. Set the x-axis as the log of the agonist concentration. Plotting the data usually shows a sigmoidal relationship. A horizontal line is drawn at 50% of the maximum response, and a vertical line is dropped down to the x-axis. Where they meet is the concentration of agonist producing 50% of the maximum response. This value is known as the EC50. For an explanation of why we do this, please see my video on how to plot a dose-response curve and measure EC50. Different agonists acting at the same receptor evoke cellular responses over a varying range of concentrations. Some are more potent and work at lower concentrations, indicated by a lower EC50 value. Other agonists are less potent and need to be present at higher concentrations to activate the receptor. They have higher EC50 values. So, EC50 values are an indicator of the potency of an agonist drug. Reports of potency often give the PEC50, which is the negative logarithm of the EC50. A higher PEC50 indicates a higher potency. Not all agonists are equally effective, even if they have the same potency. The natural or endogenous ligand for a receptor is considered to be a full agonist. When responses to other agonists are measured as a percentage of the maximum response to the natural ligand, that can show up differences in their abilities to evoke the maximum response of the full agonist. Some ligands produce a smaller maximum response. They are known as partial agonists. Other agonists might produce a larger maximum response than the natural agonist. They are called superagonists. There are also ligands that bind to the same receptor as the natural agonist, but induce the opposite effect. Drugs like that reduce the baseline or constitutive activity of the receptor, stabilizing it in its inactive form. They are known as inverse agonists. An inverse agonist is different from an antagonist, which simply binds to the receptor without affecting its basal activity or evoking a response. This property of agonists is known as efficacy. A full agonist has an efficacy of 1, while an antagonist has an efficacy of 0. Partial agonists can have efficacy anywhere between 0 and 1, while a superagonist has efficacy greater than 1, and an inverse agonist has negative efficacy. I have a separate video that explains in detail how a biased agonist works, so I will only give a general overview here. Enough, I hope, to help you appreciate what they are and how they differ from other agonists. We begin with an agonist ligand binding to its receptor. That causes a conformational change in the receptor protein, shifting it from its inactive state to an active state. That change initiates a response in the cell. But to generate that response, the receptor may activate more than one signaling pathway. These pathways can be equally activated by an agonist. But when some agonists bind to the receptor, they have a different effect on the receptor's conformation or shape. That results in only one of the signaling pathways being activated, leading to a different response in the cell. Other agonists can affect the conformation of the receptor in such a way that another signaling pathway is preferentially activated, again leading to a different cellular response. So, the definition of a biased agonist is that it binds to the orthosteric site on the receptor, but only activates certain signaling pathways instead of all the pathways that the receptor is capable of affecting. This time, the main agonist can't access its binding site in the receptor when it's in its inactive state. A co-agonist is a molecule that has no direct effect on the function of the receptor, neither activating it nor inhibiting it. But when the co-agonist is bound, it causes a conformational change in the receptor that frees up the binding site for the main agonist, which is now able to access its binding site and activate the receptor to produce a response. You now know the basic properties of drugs that act as agonists at receptors to initiate a biological response. They can be full, partial, inverse, biased, super or co-agonists. Each receptor has a specific structure and agonist binding sites, so only certain agonists can bind to and activate them. The types of agonists that can stimulate a given receptor varies. For example, an inverse agonist is only possible when there is constitutive or resting activity in the receptor. Co-agonists are not necessary for most agonists to work at most receptors, but they are required when the receptor has multiple binding sites that need to be occupied before they will activate. An example is the NMDA receptor, which can only be activated by glutamate in the presence of glycine.